You have an array of numbers, and you look at every possible group of 3 elements from it, where the same element can repeat in the group and order doesn't matter beyond going left to right. For each group, you combine the 3 numbers using the XOR operation to get a result. The task is to count how many different results you can get across all these groups. Beginner level. Let's start with something surprising. Imagine a list of 1500 numbers. If you pick any 3 of them and combine them with an operation called XOR, you'd guess there could be millions of different results. There aren't anywhere near that many. By the end of this video, you'll understand exactly why, and it's simpler than it sounds. Let's go step by step. Before we dive in, here's why this matters. Problems like this show up in real coding interviews at companies like Google and Bloomberg. XOR isn't just a puzzle trick either. It's used in real computer systems to check if data got corrupted. Don't worry if that sounds abstract right now. By the end, you'll recognize this pattern instantly. Let's slow down and understand the actual problem. We're going to pick 3 positions in our list of numbers, and we are allowed to pick the same position more than once. Then we combine the 3 numbers we picked using something called XOR. Don't worry, we'll explain exactly what that does in a moment. Our job is just to count. Out of every possible way to pick 3 numbers, how many different results can we get? 2 ideas will carry us through this whole video, so let's make sure they're crystal clear. First, a set is just a container that automatically refuses duplicates like a guest list at a party. If a name is already written down, writing it again does nothing. Second, XOR, written as this little caret symbol, is a way of combining 2 numbers. Think of it like a light switch. Combining a value with the exact same value flips things off back to 0, and combining 2 different values flips things off back to 0, and combining 2 different values flips something on. We'll see it in action shortly. Here's the first idea most beginners reach for, and honestly, it's a totally reasonable place to start. Just try every single combination of 3 positions directly, with 3 loops inside each other. Picture a room of people all shaking hands with each other. With 10 people, checking every handshake is instant. But with 1500 people, that's over 3 billion handshakes to check. Your computer would sit there for a very long time. We need something smarter. Here's the clever idea that saves us. Instead of checking every triple directly, we build our answer in 3 small steps. Step 1. Remove duplicate numbers, since a repeated number can't create any new result. Step 2. Combine every pair of the remaining unique numbers with XOR and collect all those results. Step 3. Take that whole collection of pair results and combine each one with the unique numbers one more time using XOR. That final collection is our answer. It sounds like more steps, what XOR is our answer. It sounds like more steps, but each step is fast and together they are much faster than checking every triple directly vaguely. Let's write this in code, one small piece at a time. First line, we turn our list into a set, which, remember from earlier, automatically throws away any duplicate numbers. Why bother? Because 2 identical numbers combined with XOR 2, 2, XOR 2, XOR 2, 0. So keeping duplicates around would only waste time without ever giving us a new answer. Second line, we go through every pair of these unique numbers, including pairing a number with itself, combine each pair with any duplicate numbers. Including pairing a number with itself, combine each pair with XOR and store every result in a new set called XOR, just cancel out to 0. Now for the final step. We take every result we found in XOR 2 to remember, those came from combining 2 numbers, and we combine each one with every unique original number one more time. This effectively simulates combining 3 numbers together without ever writing 3 nested loops. And since we are storing everything in a set, any duplicate results automatically disappear. So the number of items left in this final set is exactly the answer we want. The count of distinct results. Here's the piece that makes everything click, so let's go slowly. Computers store numbers in bits, which are just tiny switches that are either 0 or 1. Any number smaller than 1500 can be written using only 11 of these bits. And here's the key fact. When you XOR numbers together, the result can never need more bits than the numbers you started with. So every possible XOR result must be smaller than 2048. That means our middle collection, XOR 2, can never contain more than 2048 different values, no matter how huge our original list is. And that's exactly why the final step stays fast. Let's test your understanding with a tiny example before I reveal the answer. Suppose our list is just 2 2s, 2 2 2. Pause the video for a second and think. If every number you can pick is the same value, how many different results do you think you could possibly get? Quick reassurance for beginners, you do not always need the clever trick we just learned. If you're just writing a small script for yourself with a short list, the simple triple loop from earlier works perfectly fine and is much easier to read and trust. Save the stage set trick for when your list starts approaching the problem's real limit, like 1500. So, to be clear, the brute force approach from earlier, the three nested loops, isn't wrong. It's simple and it's easy to check by hand that it works. If I were writing a quick throwaway script, I'd honestly just use that. It only becomes a problem once your list size gets close to the upper limits this problem allows. Let's talk about speed in simple terms. Big O notation is just a way of describing how much slower your code gets as your input grows. The brute force method is what we call n cubed, meaning if your list has 1500 numbers, you do over 3 billion operations. Way too slow. Our stage set method is roughly n squared for the pairing step, which is much smaller, and the final step is capped, thanks to that 2048 limit we found earlier. The lesson to remember, whenever a problem tells you the individual values are small either. Let's double check our code handles the small tricky cases correctly. If the list has just one element, our unique set has one value, the pair set has one value, and the final set has one value, so it correctly returns 1. If every number in the list is a duplicate of each other, everything collapses down the same way. And no matter how big the list gets, up to 1500 entries, that middle set we talked about never grows past 2048. So this solution stays safe and fast 2048. So this solution stays safe and fast in every case. Let's recap everything we learned today, step by step. We removed duplicate numbers first, then combined pairs with XOR, then combined those results with the original numbers one more time to reach every possible triple combination. Remember our little 2-2 example? That's a perfect illustration of how, when the range of possible values is small, the range of possible answers is small. The range of possible answers is small, too. That's the whole secret. This same idea works for pairs of numbers, not just triples. Great job following along. Tomorrow's video tackles a harder graph problem using this exact same bounded range idea. Intermediate level. Pick any three numbers from an array of 1500 and XOR them together. You'd think there could be millions of different answers. There aren't. Stick around and I'll show you exactly why. XOR problems like this show up a lot in interviews at places like Google and Bloomberg because XOR underlies real systems, checksums, parity bits, even gray codes. By the end of this video, you will spot the bounded range trick instantly whenever you see XOR plus small value limits. We pick three indices, I, j, k, where I is less than or equal to j, which is less than or equal to k, so an index can repeat. We XOR those three values together, and we want to know how many different results are possible across every choice. Think of a set like a guest list at the door. If your name's already on it, you don't get added twice. XOR works like a light switch between two bits. Flip the same value against itself and it goes off. Flip a different value and it turns on. Those two ideas are all we need to build our answer. The obvious move is three nested loops trying every I, j, k, like checking every possible handshake in a room. With 10 people, that's instant. With 1500, it's over 3 billion handshakes and your program just sits there spinning. Here's the trick. Instead of enumerating every triple directly, we build up reachable XOR values in two stages. First, we get every possible two-value XOR. Then we XOR that whole set against the original values one more time to get every three-value XOR. We dedupe nums into a set first because duplicate values can never create a new XOR result. They're just wasted work. Then we XOR every unique pair, including a value with itself, and collect the results in another set. Now we take every two-value XOR we found and XOR it with every unique original value one more time. Since sets drop duplicates, the size of this final set is exactly the count of distinct triplet XOR values we need. Here's the click moment. Since every value is under 1500, it fits in just 11 bits, so any XOR of them is under 2048. That means XOR 2 can never grow past 2048 entries, so step 3 is always fast, no matter how big the array is. Clean. Quick pause before I show you. What does this return for the array 2 do? Think about every possible triple you could form. If you're writing a quick one-off script on a small list, don't bother with the stage set trick. The triple loop is easier to trust and just as fast in practice. The moment you see n creeping toward the problem's stated limit, that's your cue to switch. The alternative is the brute force triple loop from earlier. It's dead simple and easy to verify by hand. My honest opinion, for a quick script on a small dataset, brute force is totally fine. I wouldn't over-engineer it, but it has no place once n gets anywhere near this problem's limit. Brute force is order n cubed, which at 1500 is over 3 billion operations. Way too slow. The stage set approach is roughly order n squared for building the pairs, then a fixed small step after, because the second set is capped at 2048. Whenever a problem bounds the values instead of just the array length, that's your signal to build the reachable set in stages instead of looping over every combination. With just one element, unique has one value, XOR2 has one value, and the final set has one value, so it returns 1 correctly. Whether the array has one element or 1500, the middle set never exceeds 2048. So nothing here ever slows down or breaks. We dedupe the array, build every pairwise XOR, then XOR that set against the values once more to land on every triplet XOR. Remember that two example that broke brute force intuition for a second. The bounded value range is exactly why it stayed simple. New Delhi drops tomorrow, same time, where this same bounded range trick cracks a much harder graph problem. Some code is unreadable. This button is unreadable. At bonds level. You already know where this is going, 500 elements, own 3 triples, but the answer space is capped because XOR of bounded values is bounded. The interesting part is in the observation. It's how tight that bound actually is, and how it changes your complexity analysis. This is the standard value range bounds. The reserved space pattern. Same family as counting distinct subarray XORs or bit mask DP over small alphabets. If you've done gray code or CRC work, you already have the intuition. The interview question is really testing whether you reach for range-bounded enumeration instead of defaulting to combinatorial search. IJJK with repeats allowed just means count distinct values reachable as an XOR of a multiset of size 1, 2, or 3 from the array. Since repeated indices with the same value contribute nothing new, this collapses to a reachability question over the dedupe value set. Nothing new here, hash set for Dedupe, XOR as its own inverse. The only thing worth flagging, because ATA0, self-pairing never adds new reachable values, which is why deduping first is safe and not just an optimization. On the 3, print for B, iterations at N9 1500. You know this fails before you write it. The real question an interviewer wants is, what invariant lets you avoid enumerating triples at all? This is closure under XOR, computed incrementally, reachable in once reachable, into least reachable in 3. It generalizes directly. If the problem asks for k tuples instead of triples, you just iterate this closure step k1 times. And each step's cost is bounded by unique x reachable setting, not by combinations of indices. Dedupe first because XOR only cares about distinct operands. Duplicate values are redundant generators, not just wasted cycles. Note XOR2 is built as a full unique x unique pass. It's technically OU2, but U is bounded by min-n, 2 bits, which matters more than n itself once values are small. One more closure pass. Worth noting, XOR3 is a superset closure, not a fresh construction. It necessarily contains XOR2 pick B0, conceptually, or any AGA self-cancel, so the count only ever grows or stays flat as you add stages, never shrinks. The real complexity here is ON to dedupe plus OU2 to build XOR2. But U is capped by 2nc log to 15c100 regardless of how large n gets. That's the crux. Past a certain n, you're not bounded by array size anymore. You're bounded by the bit width of the value domain. The same reasoning you'd apply to bitmask DP state spaces. Trivial case, but it's the one that trips up a naive combinatorial mental model. Dedupe collapses this to a single element domain instantly. So the answer is 1. Good sanity check for your closure logic before you trust it on adversarial input. Constant factor argument for small n, the OU2 stage approach isn't necessarily faster in wall clock terms since it does full pairwise products rather than triangular ones like the brute force. Reach for the stage version specific key once n approaches the bound where cubic blows up, not by default. Follow up, an interviewer might ask, what if values weren't bounded, just the array length? Then this closure trick loses its guarantee and you're back to needing the actual bound on distinct achievable XORs, which without a value cap could genuinely be ON or worse. Words stating that dependency explicitly rather than assuming it always applies. More precisely, ON for dedupe plus OMIN now, 2 for ace 2 for SOR2 plus OMIN now, 2 for ace x min now, 2 for ace for SOR3. Space is O2 for 8s, regardless of n. The general principle to carry into other problems, whenever a problem caps values x rather than count, look for whether the reachable set size is what's actually bounded and build closures over that set instead of over-index combination. Not much to stress test here since the closure logic is dedupe driven and self-verifying. The one thing worth confirming under adversarial input is that value range, not array length, is truly what's constrained in whatever variant you're handed. If the constraint were on n instead of value magnitude, this whole approach falls apart. Closure over a value-bounded domain, computed in K1 stages for K tuples. The transferable insight. Check whether it's the value range or the input size that's actually capped. That determines whether you can trade combinatorial search for a fixed size reachable set computation. Tomorrow's problem pushes the same idea into a harder graph setting. Subscribe if that's useful. Quick quiz. With 1500 numbers, why can't we just brute force every triple? Pause it and think for a sec. Take a moment before I give it away. 500 numbers gives over half a billion triples. Way too slow. That's why we build the pairwise XOR set first, then XOR again. Second one, why do we dedupe the array before computing pairwise XORs? Pause and think about what duplicates would do. Give it a second. Duplicate values just recompute XOR pairs you already have. The set throws them out anyway. Deduping first skips that wasted work.